Today we're going to be talking about measurement, specifically looking at the topics of precision and conversion. And I want to start by looking at an example that I always saw when I was in grade school, high school. When they would explain the concepts of precision and accuracy and the difference between them, they would show us these two targets. And they would say something like, this is low accuracy, low precision. This is low accuracy, high precision. High accuracy, low precision, and high accuracy, high precision. And I had always kind of conflated the two terms anyway in my head to be precise and to be accurate. I kind of thought were the same thing. So to see something like this, where this is, obviously not accurate at all, but they would still say that was very precise, I just didn't get it. So this example never really clicked with me. So I Googled, other examples to help me better understand it. And I came across this one, which I think helps me better appreciate the target example now, but I had to see this one first. So how I was explaining this other example is the idea of a weight scale. So suppose you have a weight scale that's very precise. Maybe it measures to every tenth or even hundredth of a pound, right? Or it's grams or whatever the units are. But the point is it's very precise. So you could measure even a few grains of sand and it would tell you how much it weighed. But suppose that the scale itself was skewed somehow. So it was always off by exactly 5 pounds. So if you weighed a little bit of sand and it was only maybe 3 ounces of sand, but it told you it's 5 pounds and 3 ounces of sand, then it would always just be off by that set amount. So you could measure whatever you wanted, but it would always be off by some amount. That would be an example of high precision, but low accuracy, because you're always missing the mark by a set amount, but you're able to measure very small things very accurately, or very precisely rather. Okay, so maybe now we can look at this example and better understand what they're trying to get at. The idea that you can miss, right? You can have data or whatever your goal is that's not accurate, but it's precise because it's all very close to each other. Okay, so precision has a lot to do with closeness. Okay, Kevin Durant is a big fan of showing us what precision looks like. Precision is, again, it just means a small window of error. So here's another example with the targets. High precision, good. Here's another word they use is trueness. Instead of accuracy, they say it's trueness. It's true to the value. High precision, good trueness. High precision, bad trueness. But again, it's good precision because all the data is close, right? It's not covering a bunch of different spaces. It's all relatively close to each other. This is good trueness because it's right on the target, but it's low precision because you've got data that's all around here, right? Covering a much wider breadth of space. And again, this would be low precision and bad trueness because, again, they're not all near each other. The data is not near each other, and it's also not hitting the target. Okay, so hopefully that helps a little bit. Here's an example with measuring to kind of get a better idea. You'll notice when we're looking at, for example, a measuring tape, we have an inch from here to here, but we also break that down into half inches, quarter inches, eighths of an inch, and sixteenths of an inch. And you could keep going if you so wanted to. But if you think about it, if I asked you to measure this bug in terms, this beetle rather, in terms of half inches, some people might say, oh, it's about a half an inch, and some people might say it's an inch. That's a pretty big window of error, right? If I said measure in terms of quarter inches, some people would say that's about 3/4 inches, some people would say that's about a full inch, right? So you can see the window of error gets a little bit smaller. If I said measure in eighths of an inch, some people would probably say it's about 7/8. Some people would say it's about an inch. So the window of error gets even smaller. And if I said measure in terms of sixteenths of an inch, the window of error would get even smaller because then all the guesses would only be about a 1/16 of an inch off. And just a tip for when you're measuring, you'll notice this isn't really set up perfectly to measure because the beetle itself, neither the legs nor its body is lined up with the actual end of the measuring tape. So if you want it to be a little bit more precise, you'd bring the legs over and bring it up. And you could see that from legs to end, it would be exactly 7/8 of an inch. If you wanted to do from the end, from body, meaning the top of its head to the end of its body, you would have closer to 13/16 of an inch. So you can see it really matters when it comes to precision what kind of units we're using. And the more precise you want to be, we need smaller units. Okay? Another skill that's very important that I didn't appreciate when I was younger was the importance of estimation, and I want to give you an example to help you think about it. So suppose you have a birthday party, right? Let's say you invite 10 friends and maybe 2 can't come, but your parents order pizza for the party, and let's say maybe they ordered 1 or 2 many pizzas, right? Or maybe they ordered 1 or 2 few. That's fine because they could just order more pizza quickly, or if there's leftovers, you can just eat 1 or 2 boxes the next day. Not a big deal. But think about the importance of estimation when it comes to a restaurant. Let's say you have an Italian restaurant and maybe 50 groups are showing up that night. And on any given night, that restaurant has to be prepared if they're, good at serving. They need to be prepared to serve everybody the same thing if that's what everybody wanted. Now, of course, you could just say this isn't on the menu on a given night, but if you're trying to please everybody, you want to make sure that you have enough supplies of everything to make sure everybody's satisfied. So if you're at this Italian restaurant, everybody orders Alfredo, or everybody orders chicken parm, or everybody orders pizza, you want to make sure that you've estimated accurately enough so that you can satisfy your customers, right? So again, if you have a small pizza party, it's, not being a great person at estimating that's fine. But you can see the importance of good estimation skills when it comes to a restaurant setting because you need to be accurate and you don't want to waste a lot of food. You don't want to be in a food shortage, but you also don't want to waste a lot. So being able to estimate accurately is super important. I want to give a couple examples to also give a better understanding of precision. And one is golf. So I don't really play. I've watched a little bit, but I got to do some virtual golf this past winter at an indoor golf place. And it was fun to appreciate the difference in precision versus power depending on the type of club you were using, right? So if you're just trying to drive the ball far and you don't really care about necessarily where it lands, obviously you want to be on the green, but you're just trying to drive it with distance, you're going to use a driver, right? But as you get closer and closer to the hole and you care more and more about precision and proximity to the hole, you might use a wedge, or if you get close enough, you might even start using your putter, right? So you can see that when I'm trying to cover great distances, I'm using the more powerful club, but when I get closer, I'm using the more precise club. Another fun example, it's still the same idea of proximity, but more conceptually. If you've never played Akinator, I highly encourage you to do so. It's a great guessing game in which this genie guy tries to figure out whatever you're thinking, and so you'll give him he'll ask you questions, right? Like, is your character a boy or a girl, fiction, nonfiction, something like that. And through this process of elimination, he's going to get more and more precise with his questions and will eliminate entire topics. So, for example, if he asks you, is your character fiction or nonfiction, and you say nonfiction, he's going to be able to wipe out millions of entries that would have been in books, comic books, TV shows, movies, etc., because he knows that if you're being honest, anyway, there's no way that certain characters could fall within your answer, okay? And then he gets more and more precise. So there's another kind of fun example of precision by whittling down to a particular topic. Another example is money, right? So if you're spending money on, penny candy, for example, we might use something smaller like single dollar bills, maybe a 5, but most likely some change is involved, right? Versus when you go to buy a car, not that you should buy a car with cash like this image shows, but just to show the point, you're going to be using much larger bills. And in reality, you're probably not even using bills. You're probably just writing a check for thousands of dollars. But you can appreciate the difference in precision between these purchases, right? This is a much more precise in the sense that it's using smaller change. This is a much grander purchase, and so you're using much bigger bills. Now we can look at image resolution. The more precise we get, right, meaning the more units that we have, this DPI means dots per inch, you can see that as I increase the dots per inch, this looks more and more like a circle. These are all technically circles, but this isn't really believable. This is certainly very close, but once you get up to 300 DPI, you're looking at a very smooth surface. And same thing down here, right? You could kind of get a vague idea that this is maybe sky and grass, and certainly once you get to here, and definitely here. But the best image is going to be once you increase those dots per inch. And again, that's with higher image resolution. The idea that was shown in this previous slide was the idea of refinement. And I don't know who painted these, some art student, but they're very good. I found it online. And you can see that his skill increased from 2020 to 2021 because he had refined his skill. He had gotten much more precise with the brush. So he was able to find certain details about his face. I'm assuming these are self-portraits, right? And he was able to refine certain details that he started to get at here, but he was able to refine even more here. And you can see also this example with the bird over here. You first start by drawing the gestures and the proportions, then you start including shapes and scale, some form refinement, and finally you add some value and texture to get the best looking image of the bird. So when we're measuring, often in math books you'll find tools like these, right? Helpful little things to think about. So for example, if you're going to measure something based on inches, it's probably pretty close to the length of a paper clip or thereabouts. A foot, maybe they say you can think about something like close to a grinder or a sub, right? That's about a foot. This one I don't necessarily agree with. The bike, I don't know many bikes that are 3 feet long, but maybe 2 yards. But anyway, a yard is 3 feet. And then a mile, if you ever go to a track and you walk it 4 times, that's equivalent to a mile. So they're saying essentially that 4 tracks is a mile. Okay. I thought it'd be fun to share some trivia. In the English system, there's other units of measure. For example, furlongs. 8 furlongs is a mile. 220 yards is a furlong. 5 feet is a pace. 125 paces is a furlong. So there's some forgotten units that we don't obviously use on a day-to-day basis. I'd not heard of these before I researched for this slideshow. But I think it's cool to note, right? But it makes us ask why, right? Why do I have something for 3 feet but not 5 feet? For a mile but not for a furlong, right? And I think because in our minds we tend to think exponentially. We don't necessarily think linearly, right? And what I mean by that is, think of a neighborhood, for example, right? You think about one family, right? And then maybe in that neighborhood there's, about 10 or so families. And then when you start talking about a whole town, you might have 100 families. But that's just kind of how we think. We think about either our own immediate group and then maybe those who are, within close proximity, and then we might think about our whole town, right? But we don't think linearly. We tend to put things into groups of one, few, and many. That's just how we think. And even with the metric system, which scales up nicely going by tens, right? A lot of people love the metric system. People complain that, we don't use it here in America. But even if you look at the metric system, yes, it's nice because it goes down by powers of 10. But even the metric system, I'm willing to bet, in countries that use it, they don't necessarily use all of these equivalently. Like certainly we use the meter and the centimeter and the millimeter and the kilometer, but I don't know a lot of things that are measured in terms of hectometers or decameters or decimeters, right? Maybe you do. But from the things that I've heard, it usually comes down to these, right? The kilometer, the meter, the centimeter, the millimeter. Because again, that's just how we think. We have something that represents the really big stuff, the maybe medium human-sized stuff, the kind of small stuff, and then you can get to like maybe the microscopic stuff. Look even at Roman numerals, for example, right? If you've ever watched the Super Bowl, you've seen some Roman numerals like LXI or LVII or LII, right? L meaning 50, I meaning 1, V meaning 5, etc. But on this system, right, they have something for 1, for 5, for 10, for 50, for 100, for 500, for 1,000. But notice there's nothing for 200 or 250 or 300. Because again, that's just not how we think. We tend to group things and then generalize from there. So here's some common conversions for imperial units. I'm sure you've seen some of these before, right? Things like 1 foot is 12 inches, a yard is 3 feet, which is 36 inches, a mile is 5,280 feet. A mile is also, if you divide that by 3, that would be 1,760 yards. There's some for volume and for weight. Particularly for measuring with the linear measurements, I have this little convention that I came up with using all H words. So if you have something that you can hold in your hand, that's probably going to be using inches. If you have something that's about the size of a human or a little bit bigger, you might use feet, right? Because we measure humans based in feet. If you have something that's around the home or even the size of the home, you could probably still use feet, but you also could use yards. And then if you have something in your hood, neighborhood, hometown, whatever word you choose to use, you're probably going to be using miles, right? So I think that's a helpful little naming convention. If it helps you, use it. If not, don't. But that's just something that helps me to keep track of when should I use inches, when should I use feet, when should I use yards, when should I use miles. And then a video I would highly suggest you watch if you haven't is Saturday Night Live. Had a great skit with Nate Bargatze in which he plays George Washington, coming up with the conventions, the measuring conventions for America, right, when they were founding our nation. And it's just funny because it really hints at the fact that a lot of our conventions for measuring are somewhat random. Right, I saw this meme that kind of hinted at it as well. It says sauce cat is now 7 sauces, right? Just showing that if you really wanted to, you could measure things in terms of anything. We have become very accustomed to inches and feet and yards and miles, etc. But the reality is that we could use any conventions we wanted to. And now I want to end with a couple examples. Converting. And a key thing to remember is that as the units get larger, the value must get smaller. Okay? As the units get larger, the value must get smaller. And as the units get smaller, the value must get larger. So here's what I mean. 1 kilometer is 10 hectometers, is 100 decameters, is 1,000 meters, is 10,000 decimeters, etc. 2 miles is 3,520 yards, is 10,560 feet, is 126,720 inches. So you see that as I get more and more precise with my units, right, smaller units, the number consequently must go up, right? And here's a helpful little image to help you understand scaling if you're going in the metric system from kilometers to meters to centimeters to millimeters or back up, okay? So for example, how many meters are in 8 kilometers? Kilometers is 1,000 times greater than a meter, so there are 8,000 meters in 8 kilometers. How many kilometers are in 5 meters? We are now increasing our units, so we must decrease the value by the same amount. 5 divided by 1,000 is 0.005. There are 0.005 kilometers in 5 meters. How many inches are in 10 feet? 12 inches are in 1 foot, so we increase the value by 12 since we are decreasing the units by 12. So we're going from 10 times 12, 120 inches. How many centimeters are in 5 kilometers? We have to shift the decimal point 5 times to the right to change the units from kilometers to centimeters, which is equivalent to dividing by 100,000. So that means that we need to increase the value of 5 by the same amount. 5 times 100,000 is 500,000 centimeters. So there are 500,000 centimeters in 5 kilometers. And there are 120 inches in 10 feet. So anyway, I hope that was helpful in understanding precision, both conceptually and also understanding conversion better in how we convert units. I hope to be putting out some more videos soon about this with some more examples, just doing more reps. But in the meantime, I hope it's helpful, and thank you for watching.